This presentation is delivered by the Stanford Center for Professional Development.
All right, so where did we leave off last time? I'm going to reiterate these things that are quirky about the last changes I was making at the end was taking an existing container class that held only strings and turning it into this template form of it that would now hold any kind of thing I wanted to stick into it. And along the way, I had to make a couple changes, and each of them actually kind of has some pitfalls in getting this a little bit wrong. And so I just want to reiterate them. There's a lot of examples of these in the textbook. So you will see, you know, all of the templates that are implemented in the chapters 9, 10, 11, and so on do have examples of this. And for this first assignment, we won't be building it as a template. So this is actually kind of more like a future thing to kind of get prepared for when you're writing a template later. But just to remind about the things that have to happen, right, is this template type name, elem type, the template header, we'll call that, gets placed sort of in all over the place when you make that change. The first place it appears is in the .h on the class interface. You'll say template type name, elem type, class, you know, vector, class stack, class whatever it is you're building. That now means that the class is a template type whose name will only really exist in the form vector angle bracket string, close angle bracket from that point on. In the .cpp, it gets repeated on every single member function definition. There's not one overarching kind of scope around all of those. Each of those has its own little independent setup for the scope, and then it has this additional sort of goo that needs to go on it about, oh, it's the template form of the member function size that is based on the vector class template. So you'll have to kind of get this all over the place. And then the scope of the class, right, its new name is now whatever your original class name was, but with the angle bracket elem type, : : There is no longer a vector unadorned once you've made that change. And so when the client uses it, you'll always see that, and even on the scope resolution that's being used, even in the member functions themselves have the same adornment. And then elem type gets used everywhere you would have otherwise said it's storing strings. This is a string argument, this is a string return type, this is a local variable that's string, this is a data member that is a array of strings, whatever, all those places, right, where you were saying, you were earlier committing to a precise type, right, you're going to now use elem type everywhere. It's pretty easy to do it in like 9 out of 10 places you need to do it and leave one of them out. And the funny effect of that will be that sometimes it'll go unnoticed for a while because let's say you wrote it as a vector of strings originally. You changed it to be a vector template. You left one of the places where there should have been an element type still says string. But then you keep testing on vectors of string because you happen to have a lot of vector string code lying around that you were earlier using. And what happens is you're instantiating the vector with string, and it's kind of, the mistake is actually being hidden, right? Because the one place where it's wrong, it happens to be exactly string, which is what you're testing against. And it was only when you went out of your way to then put vectors of int that you would suddenly get this type mismatch in the middle of the code where it says, oh, here's this place where you're declaring a variable of string and you're trying to put an integer into it or something, or you're trying to have an array that's declared as integers and it really needs to hold, it's declared to hold strings and it really needs to hold ints. And so one way to shake that out early is actually to be sure that whatever testing code you're doing on one type, you also do it again on a different type to make sure that you haven't accidentally got some subtle thing hiding in there. And then this last thing is about how the templates are compiled, which is truthfully just a quirky behavior of the way C++ requires things to be done based on how the compiler's implemented. That the template, right, is not compiled normally. So all normal files, you've got random.cpp and main.cpp and boggle.cpp. You always put those in the project, and that tells the IDE you want this one compiled. It says, please compile this and link this in with all the code. Once you have code that is templatized in here, you don't want it to be compiled in advance. It can't be compiled in advance is really the problem. That looking at that code only describes the pattern from which to build vectors, not how to build one vector and compile it for all intents and purposes. It's on the fly going to make new vector string, vector int, vector bool. So we pull it out of the project. We remove it, so we don't want the compiler trying to do something with it in advance. For some compilers, actually, you can leave it there and it'll be ignored. The better rule to get used to, though, is just take it out, because some compilers can't cope with it. You don't want to actually get in any bad habits. Pull it out. It no longer is compiled like an ordinary implementation file. You then change your header file to bring in that code into the visible interface space here at the very end by doing this pound include of a .cpp file. In no other situation would you ever want to pound include a .cpp file. So as a habit, I'm almost giving you a little bit of a bad one here. Do not assume this means that in any other situation you do this. It is only in this one situation of I have a template class, this is the header for it, it needs to see the implementation body as part of the pattern to be able to generate on the fly the client's particular types, and this is the way we're getting the code in there. The way I would say most library implementations, sort of standard implementations in C++ do this, is they just don't bother with having a separation in the .h and the .cpp at all. They just put everything into the .h to begin with, and they don't even pretend that there is an interface separated from the implementation. That's sort of sad because in some sense that interface implementation split is an important part of psychologically of how you're thinking about the code and what you're doing, and I think jamming them together in the same file, right, clouds that separation that we considered so important. But that is probably the most practical way to handle this, because then it just doesn't, you don't have problems with thinking you can compile this and having to muck with this pound include of a CPP, which is weird. So you'll see it done the other way in other situations too. All right, so that was just like, I wanted to reiterate those because those are all, you know, little quirky things that are worth having somebody tell you and having to find them out the hard way by trial and error. Any questions about kind of template goo? Well, this is like the biggest class I've had in years. What do you guys, like, is this midterm day? Was that why you guys are all here? Or just because you heard I was going to dress in a skirt and you wanted to see it? like 3 times as many people as we always have. I'm going to code. I'm going to code on my new computer. Do you see my new fancy computer? It's like, I like it when we just code. I feel, you know, like when I do it on the slides, I always feel like it's so dry and so boring, and it looks like it just, you know, came out of nowhere. It's good to kind of see it in real time and watch the mistakes we made live. So what we're going to do over here is we've got the my vector that we were working on last time. So it's got a skeletal interface, right? It has size, add, get, set at, and some of the other functions are missing. The ones like clear and insert at and remove at, and the overloaded bracket operator and things like that are not there. Okay. But as it is, it does work. In our simple test right here, we put 9, 10, 1, and then we printed them back out. So let's just go ahead and run that to see that if I put a 9, 10, and a 1, and I iterate over what I got there using the get at and size, it seems like it has put 10 things, these 3 things in and can get them back out. Okay. Now, I'm going to show you something that's going to make us a little bit sad, and then we're going to have to figure out how to fix it. That there is behavior in C++ for any class that you declare that unless you state otherwise, that it's capable of assigning from one to another, making a copy. So all I added here at the bottom was another vector called W, who, I should make this size a little bigger. The screen is, I think, a little different than my other resolution, so let's crank that number up. Make it a little easier to see what we're doing. Okay. I declared a new my vector, also of int type. Its name is W, and I said W equals V. So this is actually true of all types that you declare in C++, that by default they have a default version of what we call the assignment operator that does kind of what's you can imagine is a member-wise copy of V onto W. So that works for structs. Think about it in the simple case of a struct. If you have a struct with X and Y fields and you set this one to 0, 0, and then you have point 1 has set the X and Y to 0, 0, and you say point 2 equals point 1, it copies over the X and Y values. So you end up with 2 points who have the same field values, whatever they were, right? The same numbers. The same thing is true of classes. That unless you state otherwise, if you copy one instance, one object on top of another, it copies the values of the fields. Okay, let's look at the fields to see how this is going to work for us. The fields in my vector right now are a pointer to a dynamic array out here, 2 integers that are recording how many slots are used in that array and what its capacity is, and then there's no other data members. We have 3 data members. So when I have made my V and my W, each of them has the space for 1 pointer here at the top, and then these 2 integers. And then the first one, right, if you remember a little bit how the code works, it allocated it to some default size. I don't remember what it was. Maybe it's 10 or something. And then it fills it up from left to right. So the first one I had, I'm going to put in the numbers, 1, 2, 3, let's say. So I add 1, I add a 2, I add a 3. Then the number used will be 3, and let's say the number allocated is 10. So this is num allocated, this is num used. Okay. So subsequent, things being added to that array will get added at the end. We know what our bounds are and all this sort of stuff. Okay. Now I say W in my code. I say, oh yeah, it's like just declare W. Well, W's constructor builds it a 10-member array, sets the num allocated to 10, sets the num used to 0, and it's got kind of the empty, ready to go vector to put things into. When I say W equals V, it's just going to take these fields kind of one by one and overwrite the ones that were in W. Let's watch how that works out. So we copy the num allocated over the num allocated. 10 got written on 10. Okay. We write the num used on top of the num used. Okay. And then we copy the pointer on top of the pointer. This is pointer assignment. This is not doing any what we think of as a deep copy. It's a shallow copy or an alias. That means that W no longer points to here. Its ARR points to there. All right, this can't be good, right? If you look at this picture, you've already got to be worried about where this is heading. Just immediately you will notice that this thing orphaned, right? No one's holding on to this. This thing's hanging out in the heap. This guy's dead in the water. Okay, so we've lost some memory. That in itself doesn't sound terrible. But now we have V and W both pointing to the same array. They have the same values for these two things, but they're actually independent. And now it is likely that if we were to continue on and start using V and W, we're going to see some really strange effects of the two of them interfering with each other. So for example, if I do a V dot set at, well, let's do W for that matter. So I say W dot set at index 0, the number 100. So W says, check and make sure that's in bounds. It says, oh yeah, the index 0 is, within, it's greater than or equal to 0. It's less than my size. Okay, and this is go in and write 100 in there. As a result, it turns out V.getAt also changed. And that would be pretty surprising, right, that these happen. So now they're just colliding. There's one piece of memory that's being, shared between the two of them. And when I change one of them, I'm changing both of them. They are not independent. They now have a relationship based on this assignment that's going to kind of track together. There are actually worse consequences of that than that. So this looks kind of innocent so far. Not innocent isn't the word, but at least it's the opportunity for malicious error still seems like, well, okay, you have these values that are changing. The really terrible situation would happen when, let's say V keeps growing. They keep adding more things. So they add the numbers 4, 5, 6, 7, 8, 9, and then it fills up. So it has num used as 10, num allocated as 10, and it goes through and it says, oh, it's time to grow. I want to add an 11. And the process of growing, if you'll remember, was to build an array that was twice as long, copy over the front values, and so copy up to here, have this back half uninitialized, and then deallocate the other one. So delete this piece of memory, and then update your pointer to point to this new one that now is allocated to a length of 20. Okay, when you did that, right, W just got screwed. Right, W points to this piece of memory that you just took away. And then you will be much more sad than just getting a junk value out or a surprisingly changed value out. Now if you ask W to go get the value at position 0, all bets are off, right? It might happen to work. It probably will work for a little while, but at some point this memory will get reclaimed and reused and be in process for something else, right? And you'll have completely very random-looking, undetermined results from access to that W. So this really just can't exist, right? We do not want it to be the case that this default member-wise assignment goes through. It will do us no good. So in the case for objects where member-wise copying, right, is not what you want, you have to go out of your way to do something about it. The two main strategies for this is to really implement a version of assignment operator that will do a deep copy. That's actually what our ADTs do. So the vector and the map and the stack and the queue are set up to where if you say v equals w, it makes a full copy, and that full copy means go take the piece of memory, get another new piece of memory that big, copy over all the contents, and so then you end up with two things that have the same number of elements in the same order, but in new places in memory. They're actually fully duplicated from here to there. And at that point, right, V and W don't have any relationship, right, that is going to be surprising or quirky in the future. They just happen to get cloned and then move from there. That's the way kind of a professional sort of style library would do it. What I'm going to show you instead, because I don't really want you to learn all the goopy things about how to make that work, is I'm going to show you how to just disallow that copying, to make it to where that it's an error for you to attempt to copy V onto W or W onto V by basically taking the assignment operator and making it inaccessible, making it private. So I'm going to show you how I'm going to do that. First I'll just show you that the truth about these kind of errors. And these errors would be really frustrating and hard to track down, so you just don't want to actually mess with this. If I have W equals V here, and then I say W.set at 0 is 100. So I was supposed to put in the numbers. Let me go. Numbers I know what to look for. I'm going to put in 1, 2, and 3. I change it in W, and then I write another for loop here that should print out the values again. And this is where I'm going to see. So I had 1, 2, 3, now I have 100, 2, 3. And then actually I'm even seeing an error here at the end where it's saying that there was a double free at the end. The free is kind of the internal name for the deallocation function. And in this case what happened is that the destructor for V and W were both being called as I exited scope. They both tried to delete their pointer. So one of them deleted it, and then the second one went to delete it, and the libraries were complaining. It said, you've already deleted this piece of memory. You can't delete it twice. It doesn't make sense. You must have some error. So in fact, we're even getting a little bit of helpful runtime information from what happened that might help us point down to what we need to do. So let me go and make it stop compiling. So there is a header file in our set of libraries that's called disallow copy. And the only thing that is in disallow copy is this one thing that's called a macro. It's kind of unfortunate that it has to be done that way. Well, I can't find the header file. That's fine. I'll just tell you what it is. And it looks like this. And I say disallow underbar copying in all capital letters, and then I put in parentheses the name of the class that I'm attempting to disallow copying on. You can have a semicolon at the end of this or not, it doesn't matter actually. I'll put one just because it maybe looks more normal to see it that way. And by doing this in conjunction with that header file, it's bringing in the macro that says put into the private, so we always put this in the private section. So we go to the private section of our class, we put this disallow copying macro in here, and what this will expand to is the right mojo. There's a sort of a little bit of a magic incantation that needs to be generated, and this is going to do it for you, that will make it such that any attempt to clone a vector using that member-wise copy, and so that would happen both in direct assignment from V to W or in the cases where copies are made like in passing by value or returning by value. Those actually are copy situations as well, that it will make all of those things illegal. It will take the standard default behaviors for that and make them private and inaccessible and throw errors basically so that you just can't use them. And if I go back to, having made this change, I go back to the code that was trying to do this, and I'll take out the rest of the code just so we don't have to look at it. That it's going to give me this error, and it's going to say that in this context, the error is over here, that the const my vector, and there's just a bunch of goo there, but it's saying that the operator equals is the key part of that, is private in this context. And so it's telling you that there is no assignment operator that allows one my vector to be assigned to another my vector. And so any attempt by the client to make one of those copies, either from passing, returning, assigning, will just balk right then and there and not let the kind of bad thing happen that then we'll just have all sorts of other following errors that we would not want to have to debug by hand. So this will become your mantra, right, for any class that has member-wise variables to where copying them in a naive way, right, would produce unintended effects. So if all the variables in here were all integers or strings or for that matter vectors or other things of that you know have true deep copying behavior, then you don't need to go out of your way to disallow copying. As long as each of the members that's here, that if you were to do an assignment from one variable of this type to the other, it would have the right effect, then you don't need to disallow. But as soon as you have one or more variables where making a simple assignment of it to another variable of that type would create some sort of long-term problem between those two objects, you want to disallow that copying and not let that bad thing happen. So things that have a linked list in them, things that have pointers in them, dynamic arrays in them, will all need this protection to avoid getting into that situation. Question?
Could you somehow overload the assignment operator?
You certainly can. So that's kind of the first strategy I said, which is like, well, you can make them deep copy is the alternative. So one way is to say, well, the shallow copy is wrong. What are you going to do about it? So I'm saying, don't let shallow copy happen. The other alternative is to replace shallow copy with a real deep copy. That's what ours do. If you're interested to look at that, you can look at our code and see what we do. It just goes through. You can imagine what it would take. It's like, okay, get some information from here, make a new array, copy the things over, right? And then at that point, you will be able to continue on with two things that are cloned from each other but no longer have any relationships that would cause problems. It's not that it's that hard, but the syntax for it is a little bit goopy. It requires some C++ we're not going to see. So you can look at it. If you want to ask Keith of 106L, he will tell you everything you want to know. Any questions about over here?
So the thing inside of disallowing copying can be anything. It can be one of the variables you declare.
So typically it'll be the name of a class.
But it could be like if you just have a variable inside your class, you don't want people to be able to copy if you just put that in.
Well, it doesn't really work that way, right? The disallow copying is saying I'm taking this type and making it not able to be copied, and so it is an operation that applies to a type, not to a variable. And so in this case, the name here is the name of the class who we are restricting assignment between things of my vector type. And so it really is a type name, not a variable name. If I said disallow copying of like ARR or num used, it actually won't make sense. It'll expand to something that the compiler won't even accept. It says, I don't know what you're talking about. Like, it expects a type name in that capacity. It says what thing cannot be copied. It is things that are of my vector type. So there's not a way to say you can't copy this field by itself or something like that. It's all or nothing. You can copy one of these objects or you can not copy it. And once you have some field that won't copy correctly without help, you're going to want to probably disallow the copying to avoid getting into trouble. All right, so you got vector. Vector's a good thing. I'm going to add one more member function to vector before I go away, which is insert at. The insert at one is allows you to place something in an index in the what should I just copy? There we go. Insert at index and an element type. So if the index is before the beginning or off the end, right, I'll raise the same out of bounds error. So I just picked up that piece of code from there. I also need to have this little line, which is if the number of elements used is equal to the capacity, right, then we need to make more space. So just like the case where we're adding to the end, if we're already at capacity, no matter where we're inserting, right, we have to make some more space. So we go ahead and do that initial step of checking to see if we're at capacity and enlarging in place. Once we're sure we have at least enough room, we're going to move everybody over. So I'm going to run a for loop that goes from size -1 to, whoops, I need an I on that. Is greater than index. Actually, I want it to be greater than or equal to index. And I'm going to move everything from index over in my array. And then array of index equals E. When we think about this, make sure I got the right bounds on this, right? This is taking the last element in the array, it's at position size -1, and then it's moving it over by 1, so it's reading from the left side and moving it over by 1, and it should do that all the way down until the last iteration, right, should be that I is exactly equal to index, and so it should move the thing out of the index slot to the index +1 slot. So along the way, moving everybody else there. Why did I run that loop backwards? I'd overwrite them the other way, right? If I try to do it the other way, I try to copy, I have the numbers, 4, 5, and 6 in here, and I'm planning on inserting at 0, right? I can't start from the beginning and move 4 on top of the 5, right? And then on top of that, right, without making kind of a mess of things. So it's actually, I can make that work, but it's definitely sort of messier. It's sort of easier to think about it. Say, oh, well, just move the 6 over, then move the 5 over, then move the 4 over, and then write your new element in the front. And so when I'm done, I do that. And so I have insert at, and I could probably test it to make sure that it does what it's supposed to do. v.insert at position 0, put a 4 in the front, and then move this loop down here. So I have 1, 2, 3, and then I put a 4 in the front. Oh, look at that. Something didn't work. Want to take a look at that with me? 4, 1, 2. What happened to my 3? Where did my 3 go? Why did I lose my 3? How does it know how many elements are in the vector? It's keeping track of that with num used. If you look down here, for example, at add, when it sticks it in the last slot, right, it updates the num used in increments of by 1. I wasn't doing that over here in insert, right? And as a result, it didn't, it's an admirable job. It moved all the numbers over, but that it never incremented its internal counter, so it thinks actually there's just exactly still 3 elements in there. So I better put in my num used plus plus in there too. 4, 1, 2, 3. So my number was there. I just wasn't looking at it. It was just a little bit further in the array. Okay. All right. So with that piece of code in, I think we're in a position to kind of judge the entire strategy of using a dynamic array to back the vector. The remove at operation, right, is similar in terms of needing to do that shuffle, just does it in the other direction. And then we have seen the other operations like set at and add and get at, and how they're able to directly index into the vector and kind of overwrite some contents, return some contents. And so you kind of get a feel for what is it that an array is good at, what things it does well, right, and what things it does poorly. So a vector, right, is an abstraction. You offer up to somebody a vector. It's a list of things. That the trade-offs that this implementation of vector is making is it's assuming that what you most care about is that direct access to anything in the vector, because that's what arrays are good at. It is a trivial operation to say start at the beginning and access the nth member, because it just does a little bit of math. It takes the starting address in memory and it says, oh, where's the 10th member? It's 10 positions over in memory. And so it can do that calculation in no time and then just directly access that piece of memory. So if what you are really concerned about is its ability to retrieve things or update things in that vector, no matter where you're talking about, the front, the back, the middle, in constant O of 1 time, right, this design is very good for that. What are the operations it's going to actually bog down on? What is it bad at? When do you see sort of the consequences, let's say, of it being in contiguous memory being a disadvantage rather than an advantage? Adding something where?
At the beginning.
At the beginning. Certainly any operation like this one, the insert at or the remove at, that's operating in the front of the array is doing a big shuffle. Things forward, things back to make that space, to close down that gap. And so for an array of large enough size, right, you'd start to notice that. You have an array of 1,000, 10,000, 100,000. You start inserting at the beginning, you're going to see this cost of the insert, shuffling everything down, taking time, right, relative, in this case, linear, right, in the number of elements that are being moved, which on average, if you figure you're inserting kind of randomly in positions, right, could be half of the elements or more are going to need to move. It also actually pays a little cost in the resizing operation. That happens more infrequently, the idea that as you get to capacity, right, you're growing. In this case, we're doubling. So we're only seeing that kind of at infrequent intervals, especially as that size gets large. Once you get to 1,000, right, it'll grow once into be 2,000. Well, then it'll grow once to be 4,000. So you'll have a lot of inserts before you'll see that subsequent resize operation. But every now and then, right, there'll be a little bit of a glitch in the resize where you might say, I'm adding, especially if you're adding at the end. Adding at the end is easy. It increments the num use, sticks it at the end. But once every blue moon, right, it'll be a long time as it copies, and then you'll go back to being fast, 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 fast till you exhaust that capacity, and then again, every now and then, right, a little bit of a hiccup when it takes the time to do the resizing. Overall, the number of inserts, right, that cost can kind of be averaged out to be considered small enough that you would say, well, amortized over all 1,000 inserts it took before I had to copy the 1,000 when I grew to 2,000, each of them paid, 1/1000th of that cost, which ended up making it come out to, and on average, still a constant cost, is one way that we often look at those analyses. So this tells you that there are certain things that the array is very good at, right? It has very little additional memory overhead, other than the additional space we're kind of storing in the capacity when we enlarge. There really isn't any per element storage that's used in addition to the number or the string or whatever it is we're storing itself. So it has very low housekeeping associated with it, and it does some things very well, but other things a little less efficiently because of having to stick it in memory, right, meant we had to kind of do this shuffling and rearranging. So the other main alternative, right, you could use for a vector is a linked list. I'm actually not going to go through the implementation of it because I'm actually going to do stack as a linked list instead. But it is interesting to think about if you just sort of imagine, if I instead backed vector with a linked list, first of all, could I implement all the same operations? Like, is it possible, right, to use a linked list? Can it do the job if I'm determined? Like, what will it take, for example, to get the element at the nth position from a linked list design? How do you know where the nth element of a linked list is? At the front of the list, Help me out.
You have to actually dereference the pointers n times.
That's exactly what you got to do. You got to walk, right? You got to start at the beginning and say, okay, you're 0, and after you is 1, and after that's 2, and so you're going to walk. You're going to do n, arrow next, right, to work your way down. You will start at the beginning, and we're going to learn some new vocabulary while we're here. So that means that accessing, for example, at the end of the list, right, is going to be an expensive proposition. In fact, every operation, right, that accesses anything past the beginning is doing a walk all the way down. And so if you plan on, for example, on just printing the list, right, or averaging the list, or searching the list, right, each of those things is going, give me the 0th, give me the next, give me the 3rd. It's going to just keep walking from the beginning each time, right? Like it's going to turn what could have been a linear operation into n squared because of all those start at the beginning and walk your way back down. So for most common uses of a vector, that would be so devastating that you just wouldn't even really take it seriously. That if every time you went to get something out of it or set something into it, you had to make this enormous traversal from the front to the back, would just be debilitating in terms of performance implications. The thing that the linked list is supposed to be good at, right, is that manipulation of the memory. That the operation like insert at or remove at that's doing the shuffle, the linked list doesn't have to do. So, for example, the worst place you can insert at in a vector is 0 if it's implemented using an array, because you have to shuffle everybody over. The best place you can insert at in a linked list is actually at 0, right? Because then you just tack a new cell in the front. And then sort of further down the list, right, it's not the act of splicing the new cell in that's expensive, it was finding the position at which you needed to do the splice. So if you want to insert at halfway down the list, you have to walk down the list, and then you can do a very quick splice, but you had to get there. So it makes this, it's kind of an inverted set of trade-offs relative to the array form, but adds a bunch of memory overhead, adds a bunch of pointers, adds a bunch of allocation and deallocations. There's a bunch of code complexity, right? And in the end, you don't really get anywhere I think you'd want to be. So it's very unusual to imagine that someone would implement something like the vector using a linked list strategy, although you could. So let's talk about stack instead. I have a little stack template that I started. My stack. It's got push and pop and size on it. Okay. I'm lazy, so I'm going to do the easiest thing in terms of implementing stack. And that is to layer. Okay. So once you've built a building block as an implementer, right, there's nothing that stops you from then turning around on your next job and being a client of that building block when implementing the next thing you have to do. That it may very well be that the piece that you just built is a great help to writing the next thing, and you can build what's called a layered abstraction. That I'm ready to build stack, and I've already gone to all this trouble to build vector. It's like, well, it turns out one of the ways I could implement a stack is to use something like a vector or an array. Now I could build it on a raw array, but I happen to build something that kind of has the behaviors of a raw array, the trade-offs of a raw array, the big O of a raw array, and is actually just, manages convenience and has error checking and stuff in it. It's like, why not just use that? I'll pay a little bit of cost in terms of taking its level of indirection onto things, but it's actually going to be worth it for saving me sort of the grungier aspects of the code. So if I'm going to put a stack contents into an array, and if I were going to push A, then B, then C, right? So then the stack that I want to have would look like this, right? There's the top of the stack up here where C is the last thing on. The bottom of the stack is down here with the first thing I pushed on, which is A. I could put this in an array. Seems like the two obvious ways to do this would be, well, to put them in this way, A, B, C, or to put them in this way. Okay. So this would be the top of the stack is over here, the bottom of the stack is over there, and then down here it's inverted, right? This is the top of the stack. This is the bottom of the stack. Okay, they seem symmetric, right? At the very least. But one of those is a lot better for performance reasons. Which one is it? Do you want to go with strategy 1 or strategy 2? 1. Why do I want 1? Why?
Because you don't have to move all the...
Exactly. So if I'm ready to put my next element in, I'm ready to put D in, that in the strategy 1 here, D gets added to the end of the vector. Right? Adding to the end of the vector, easy. Right? Doesn't require any shuffling. Updates a number. Sometimes has to grow, but easiest thing to do, add to the end. In this version, right, adding to the top would mean moving everybody over, so that I have to update this to D, C, B, A, and slide everybody down. Right? So I had to do an insert and a shuffle. Bad news, right? So similarly, when I'm ready to pop something, I want to get the topmost element and I want to remove it. That the topmost element here being at the end, remove that is also fast at the very end, right? Taking the last element off, there's no shuffling required. I just decrement my num used. If I need to do it from here, I have to shuffle everybody down. So it seems that they were not totally symmetric, right? There was a reason, right? And I had to think it out and kind of do it and say, oh yeah, okay, put them at the end. So if I do that and I go over here, I'm going to finish doing the things that make it a proper template. I go and I look at my stack, and I have the things here, is that I don't have anything to do with my constructor or destructor. I'm just going to let the automatic construction and destruction of my members work, which is to say, give me a vector, delete my vector, all that happens without me doing anything. When I want to know my size, I don't know my size, but the vector does for me, so I tell the vector to do it for me. When I want to push something, I tell my vector to add it for me. I'm telling you, this is like a piece of cake. And so then I say elem type top equals elems dot get at. I can actually use back to using the real vector, so I can use anything it has. So at the last position, elems dot remove at. Return it. Almost, but not quite what I want to do, but I'll leave that there for now. And then that's the 5 member functions I wanted, right? So they're all just leveraging what the vector already does for me in terms of doing the remove. I think it's remove at, actually, the name of that member function. The add that does the growing and shifting and all this other stuff happen. Oh, good, I have a stack and I didn't have to do any work. I love that. Let's see if it works. My stack. Push. Pop one thing off of it just for see whether I actually got what I was supposed to get. Oh, I better include the right header file. I'm going to do that. Doesn't like size. Go see what I did with size that I got wrong. Size with arguments. There we go. Whatever I put, 1, 2, 3, and then I popped, and I got a 3. Hey, not bad. Not bad for 5 minutes of work. There's something this pop method though that I do want to get back to. So push actually is totally fine, right? Just delegating the authority to kind of stash the thing into the vector. Pop right now, what's going to happen if there isn't anything in the stack when you pop? Something good, something bad, something helpful? Want to find out? Well, let's find out. Never hurts to just try it. So like right now, it seems like it just, digs into the elem. So if the elem size is 0, right, there are no elements in the stack, it'll say, oh, give me the elements of -1, and then it'll try to remove at -1. I got to figure those things aren't good things. I'm hoping that we'll push one thing and then we'll pop 2 things. See how it goes. Hey, look at that. Attempt to access index -1 in a vector size 0. So that was good. It was good that we got an error from it, right? We didn't actually like just bludgeon our way through some piece of memory that we didn't own or anything crazy like that. But the error that we got probably wasn't the most helpful. That upon seeing that error, right, you might cause you to go kind of get a little bit misled. You might start looking around for where am I using a vector? Where am I making a call to vectors bracket? Like I look at my client code, right, and all I see is a use of stack. The fact that stack is implemented on vector is something I'm not supposed to know or not even supposed to be worrying about. And so having it poke its head up there might be a little less clear than if instead, right, it had its own error message. And so I can actually just go in here to my stack and say, yeah, if, right, my size is 0, error, pop empty stack. That doesn't really change the behavior in any meaningful way. It's like it still gets an error, but it gets an error in this case that's more likely to tell somebody where the trouble is and where to look for it. So start looking for pop, right, on a stack instead of expecting to go look for a vector access. So just being a little bit more bulletproof, a little bit more friendly to the client by doing that switch. And so all the operations on this stack are O of 1 right now. The add, the pop, right, are push and pop are both adding to the end of the array, which is easy to do. And so this is a pretty efficient implementation, right, and pretty easy to do because we're leveraging vector. What we're going to look at next time is like, well, what can a linked list do for us or not, right? Does it provide anything that might be interesting to look at?